Next up, let's go over a couple of examples of making use of the fundamental theorem of calculus part 1. For our first example, we're going to take the derivative of h of u is equal to the definite integral from 0 to u of the square root of t divided by t plus 1 dt. Now, when using the fundamental theorem of calculus part 1, there are a couple things to look for. This variable should match this variable that's in here, and it should be the upper bound of the integral. The lower bound should be a constant. Once you've got those two things in place, this guy is what we were referring to as g of t in the previous examples. H prime of u is simply going to be g of u, which says replace all of the t's with a u, and we're done. Fundamental theorem of calculus works out very quickly in situations like that. However, there are certain situations where it's not going to work nearly as easily. For example, if capital R of y is the definite integral from y to 2 of t cubed times the sine of t dt. Now, this isn't exactly the same situation as what we had on the previous problem because the limits of integration are reversed. However, there was a property from the previous section that says I am allowed to reverse the order of integration as long as I multiply by -1. Once you multiply by -1, it reverses those limits, and now we have a negative sign out front. A negative sign is simply a constant multiple. This function would be referred to as g of t. Now, once we differentiate, this will simply be g of y. So negative y cubed times the sine of y. Now, occasionally we are going to encounter some situations where we may need to use things like the chain rule. For example, if we had h of x is equal to the definite integral from 1 to e to the x of the natural log of t dt. Now, in a situation like this, the input is not simply going to be x, and as a result, we're going to see the chain rule take over. Now, this function is still what we would have referred to as g of t. So h prime of x is going to be equal to g of, and the thing that we're yeeting in here is going to be e to the x. So we'll see g of e to the x times, according to the chain rule, the derivative of e to the x. Now that, of course, would be the natural log of e to the x times the derivative of e to the x, which is e to the x. Simplifying the natural log of e to the x will be x times e to the x. Now, one last situation that could potentially come up is if we have two limits of integration that are both equal to, let's do capital R of x, and we'll do the definite integral from x squared to 2x of the square root of t plus 3 dt. So this again is what we would be referring to as g of t. Now, in this case, if both of the limits of integration are variables, that's going to create quite an issue. So what we're going to do is assume that in between x squared and 2x, we can come up with some sort of constant. Now, the name of the constant doesn't particularly matter. We'll just call it a for the time being. There's a property of definite integrals that says instead of going from x squared to 2x, I can simply go from x squared to a and then a to 2x. That would look like the following. X squared to a of the square root of t plus 3 dt plus the definite integral from a to 2x of the square root of t plus 3 dt. Now, this one's all set, ready to go. Our variable is the upper bound. This one we'll need to reverse the order of integration, so we'll call this negative definite integral from a to x squared of the square root of t plus 3 dt plus the definite integral from a to 2x of the square root of t plus 3 dt. In this form, we're now ready to use the fundamental theorem of calculus part 1 as well as the chain rule. So for this situation, this will be negative g of x squared, and according to the chain rule, times the derivative of x squared, plus, same thing here, g of 2x times the derivative with respect to x of 2x. So replace the t with an x squared. This will be negative square root of x squared plus 3 times 2x, plus replacing the t with a 2x, square root of 2x plus 3 times 2. Anything that you do to it after that will help simplify it algebraically, but it won't change its overall value.